Hello and welcome again to Flipped Harber for Calculus. In this video we're going to be talking about limits involving infinity. Our objectives for this lesson are to find the limit of a function as x approaches infinity, and then we're going to take a look at how to describe both vertical and horizontal asymptotes using limits. Our outline for this video, we'll take a look at the way that limits can involve infinity. We're going to take a look at vertical asymptotes. We're going to take a look at vertical asymptotes specifically from fractions, that really is rational functions. We'll take a look at some other ways to get vertical asymptotes. Then we'll move on and talk about horizontal asymptotes and how limits are involved there. And then we're going to take a look at some infinite limits being infinite. Now let's start off with a word about infinity. Infinity is an idea. Don't think of it as a number. So because it's not really a number, it gets a little bit tricky when we try to do some math with it. Specifically, when we try to go infinity minus infinity, well, is that 0? Is that 1? Is that infinity? We don't know. Or what if we took infinity and we divided by infinity? Again, is that 1? Is it 2? It kind of depends. Which infinity is bigger? I know that sounds funny, but really that's the ultimate question. So we try to avoid this stuff. We try not to do infinity minus infinity. We try not to do infinity divided by infinity. Now there are some tricks that we're going to learn later that will make some of this weird stuff possible. But for right now, we can do infinity plus infinity. So that math with infinity is okay, because basically if I take a really big whomping number and I add another really big whomping number, I'm going to get a really big whomping number. Or if I go infinity times infinity, again, that's okay because it's just going to make another really huge stinking number. But what we don't want to do is any difference or division. Now, there's basically two ways that limits can involve infinity. We can either have the limit is equal to infinity, as we have here on the top, or we can have the limit as x goes to infinity. Now that means that we're plugging bigger and bigger and bigger numbers in for x. We're plugging in 1,000, we're plugging in 1,000,000, we're plugging in 1,000 million, which is a billion, but we just keep on plugging bigger and bigger and bigger numbers in, and we're trying to look at where that is going. And it is totally possible for it to equal a number. We'll take a look at some of those. Now let's go ahead and talk about vertical asymptotes. Vertical asymptotes occur when really weird things happen. Okay, we see this a lot with fractions, and we're actually going to look at some specific ones involving fractions in a little bit. But let's talk about some graphs here. Okay, this ability to draw what we're talking about is really important in being able to understand how these vertical asymptotes are being created. So pay attention right here. We have a limit as x approaches a from the left. We have a limit as x approaches a from the right. And I have that limit from the left is equal to infinity. So what that looks like is I can do whatever I want coming up to that vertical asymptote, but then as I get to that vertical asymptote from the left, it goes up. Now, when I'm coming from the right, it's going to go down. So maybe I'll just go down. So there we see a vertical asymptote. Now, what about this thing right here? For this graph, for this function, the limit as x approaches a, well, it's different if I approach it from the left and I approach it from the right. So this limit, we say, does not exist. We don't say that it equals infinity. We don't say that it equals negative infinity, because it depends on which side you're on. Now if we take a look where we say that the limit as x approaches a is equal to infinity, that means that the graph is going up as we come from both sides. So in this case, this means that the limit is going to infinity from both the left and from the right. So our last one, the limit as x approaches a of the function is equal to a negative infinity. That means that the graph is going down as we approach this asymptote at a from both sides. Okay, let's take a look at some vertical asymptotes from fractions specifically. What I'm talking about here is a rational function. So I'm going to start off with the rational function f of x equals x minus 2 times x plus 3 on top and it's divided by x minus 1. Now, the reason we have a vertical asymptote at 1 is because that's where the fraction is giving us 0 in the bottom. We can't have that. That's mathematical gibberish to have 0 on the bottom. So, I always say that the fraction blows up there. Okay? So we're getting that vertical asymptote when the bottom equals 0. And I want to point out that this limit from the left is equal to a positive infinity. This limit from the right is equal to a negative infinity. So we cannot take the limit as x goes to 1. We can only take it as we approach 1 from the left or from the right. If we change this function a little bit, I left the top totally alone, I squared the bottom. Now take a look at it. I still have that vertical asymptote at 1 because I still am getting 0 in the bottom of the fraction, but now notice that they both point down. So this limit would exist. If I asked what is the limit as x approaches 1 of the function, this is going to equal a negative infinity because I'm approaching negative infinity from the left and from the right. Now here's one where even though I have a rational function, I have no asymptote. So why is there no vertical asymptote in this one? Well, what's happening here is that x minus 1 can cancel out. So instead of having a vertical asymptote, there is a hole right here in the graph at 1. This would be one of those hole discontinuities that we've talked about. So here's my rule of thumb. Now, my rules of thumb are a good place for me to start. I may have to still do some work to verify my rule of thumb, but here's my rule of thumb. When I see a rational function and it's all factored out in the bottom, I have this factor on the bottom of x minus 1 in all of these rational functions. When I see an odd power, like I do right here in this first one, so I have an odd power on that factor on the bottom, then I know that the graph is going to go up on one side, down on the other. Now maybe those are flipped, maybe it's going to go down on the left and up on the right. Those are details that I need to explore, but that means that the limit as x goes to 1 is not going to exist. When I see an even power, as I do in this second f of x, when I see that even power on the bottom, that means that they're both going to go down or they're both going to go up. So that means that my limit will go to either a positive infinity or a negative infinity. Again, I've got to explore it a little bit to figure out the details. When I see this rational function and that factor on the bottom can cancel, that means that there's not going to be a vertical asymptote. There's just going to be a whole discontinuity at, in this case, 1, where that bottom equals 0. Okay, so let's take a look at some other vertical asymptotes. So these are, kind of specific examples just for you to think about. When we take the limit as x approaches 0 from the right of our natural log function, it equals a negative infinity. And if you graph that function, we see that vertical asymptote of at 0, and the graph is going down to it. If you take a look at the tangent function's got vertical asymptotes all over the place. It just repeats itself every so often. And taking a look at one of those vertical asymptotes, when we approach from the left, it's a positive infinity. When we approach from the right, it's a negative infinity. And that's true of every single one of these vertical asymptotes in this function. So just some other very specific examples of vertical asymptotes. Now let's take some time to talk about horizontal asymptotes. Horizontal asymptotes happen when a function approaches a specific value, approaches a number, when larger and larger numbers are plugged in for x. Now to us as calculus people, well, when we talk about plugging larger and larger numbers in for x, we're talking about a limit as x approaches infinity, or a limit as x approaches negative infinity. So that limit as x approaches infinity means way over to the right of our graph. Or the limit as x approaches negative infinity, that means way over in the left of our graph. And it's totally possible for these limits to equal a number. We'll take a look at some. So a lot of times the function we see with horizontal asymptotes are rational functions again. They're not the only examples though. So let's evaluate a limit for a rational function. But first, here is the most basic horizontal asymptote. When you take the limit as x approaches infinity of 1 over x, what that means is that we're trying to plug in a really huge, big, nasty number in on the bottom of this simple fraction. If you take 1 divided by a billion, you get 0.00008 zeros and then a 1. Boy, that's a really small number. If you take a 1 and you divide by 100 billion, it's even smaller. If you take a 1 divided by a billion, it's an even smaller number. And what's happening is as you plug in bigger and bigger numbers, you're getting closer and closer to this idea of infinity. Remember, it's not a number, it's an idea. You get 0. So we need to hold on to this idea that 1 divided by infinity. And it really doesn't matter what number is on top, because as long as it's a number, infinity is huge. So it's always going to be huge relative to whatever number's on top. When we take a number and divide by infinity, we get 0. All right, now we're going to use that fact because now I want to try to figure out this limit. Now we have a rational function here. We have a polynomial on the top, polynomial on the bottom. And my method, if you want to call it my trick, but it's really just a method to solve this, I look through and I find my highest power of x. Now the highest power that I see on x, it actually happens in the top and in the bottom. I see a square. But if you see a cube on the top and you don't see a cube on the bottom, you see a fourth on the bottom, you don't see a fourth on the top, doesn't matter. Find your highest power. And what we're going to do is we're going to divide every single term on the top and every single term on the bottom by that highest power of x. So what that means specifically for us right here is I'm actually going to multiply by the fraction 1 over x squared, top and bottom. Now that may seem really, really weird, but some really cool stuff's going to happen here real quick. What's going to happen is, don't ever get lazy and forget to write your limits, by the way. Always, always, always keep on writing those limits until you actually use them. But back to the algebra that's going on here. When I go 3x squared over x squared, because that's what I'm doing, is I'm dividing all of these terms by x squared, some nice stuff's going to happen with that one. When I divide x by x squared, some stuff's going to happen. Maybe not nice, but some stuff's going to happen to that one. And some stuff's going to happen to this one. I'm going to do the same thing on the bottom. Now, if you don't want it to go into, as gory detail as I am doing right here, that's okay. You don't really need to write this middle step. I'm doing it for instructional purposes right now. But this is definitely a step that you can skip if you can see what's going on. Now, I'm going to cancel everything I can inside these little fractions. So my x squareds are going to cancel here and here. Now, this is just 3. Now that everything's canceled, that first term is just a 3. I can cancel this x with one of these x's, so now I have 1 over x. And I can't really cancel anything in the third term. I can cancel this x with one of these, so that'll just be 4 over x. I can cancel all of these x squares, and I can't cancel anything in the third term. So I'm going to rewrite this. I'm going to rewrite it nice and neat. So here's my big fraction, and what I have is 3 minus 1 over x minus 2 over x squared. On the bottom I have 4 over x plus 5 minus 1 over x squared. So if you can skip that middle step and just get to that one, that's fine. Now, here's the really cool stuff. Remember, when we take 1 and divide it by infinity, or if we take any number and divide it by infinity, it goes to 0. If you take, let's say, for example, 2, and divide it by infinity squared, that's 2 divided by a really huge number like, 80 bazillion squared. All of these fractions go to 0 with my limit. And my limit laws say that I can do this individually because I can take the limit of the top and the bottom separate, and then I can take the limit of all the things added up and subtracted separate. The only thing that's left, now that I've applied the limit, is a 3 on top and a 5 on bottom. So this limit, as x approaches infinity, is equal to 3/5. Now that's cool. As you plug in bigger and bigger and bigger numbers, this fraction is going to just go to 3/5. You can actually try this out with your calculator if you plug in bigger and bigger and bigger numbers for x. The only danger here is when you're plugging in, use the store feature of your calculator so that it plugs in the exact same big number every time. If you plugged in 1 billion into one of these x's and you plugged 10 billion into another x, things are not going to work out. You've got to plug the same really big number everywhere. All right, I love rules of thumb. I try to develop these to make sense of this math for stuff. So here's my rule of thumb for rational functions. If the power on the top of a rational function is higher than the power on the bottom, then that does not have a horizontal asymptote. That limit as x approaches infinity is not going to equal a number. It's actually going to equal infinity. And we're going to take a look at some of those in a second. If the power on the top is the same, then it has a horizontal asymptote at some number. That's what we just looked at. We had a power of 2 on the top and on the bottom. It goes to some number. If the power on the top is smaller, then the horizontal asymptote is always at 0. So there's my rule of thumb, even though I've got something weird grammatically right there. Okay, let's take a look at some other horizontal asymptotes. If you take the limit as x approaches negative infinity, now that's going to the extreme left of the graph, of e to the x, it has a horizontal asymptote of 0. It does not have a horizontal asymptote going the other direction. Only as you go to the left, it has a horizontal asymptote of 0. Now here's a funky one. I love ones like this. The limit as x approaches infinity of the square root of x squared plus 1 minus x is equal to 0. How in the world does that happen? Because it seems like I'm not doing much. I'm taking the square root of x squared plus 1. How is that going to 0? Well, this one is on page 130 in your book. I want you to go check it out. See how they solve this limit. See what trick they used. All right, so let's take a look at infinite limits being infinite. Okay? We have the limit as x goes to infinity. Well, sometimes, a lot of times, that equals infinity. If we plug in a really big, huge number, we get out a really big, huge number. You know, x squared. You take 10 bazillion and square it, it's just going to get even more bigger and more scarier. If you plug in a negative infinity, though, it still becomes a huge number, but it becomes a positive infinity now. That's kind of cool. Polynomials behave like this. Polynomials do not have horizontal asymptotes. Okay, so if a function does not have a horizontal asymptote, this is what it's going to do. Okay, let's take a look at something like this. The limit as x approaches infinity, x squared minus x. Do not try to go, well, that's infinity minus infinity. This is that stuff that we can't do with infinity. But what you should do is factor it. If I factor out an x, now I take the limit. Now it's infinity times infinity, which does equal infinity. All right. So that's it. It's time for you to try some of this stuff on your own. I'll see you in class, and I'll see you online.